Hello everyone, I'm Sung Kim, your TA of 312 course, and this is the tutorial video for the Tom project. The reason I decided to record this tutorial is because that I think I cannot explain all the details within a lab time. So I'm going to record this video with super detailed step-by-step information, what to do, how to implement, for you, and it is the weekly based. So once you follow my schedule, then you can have a running thing, running like a hardware. But even though it's not complete, but at least it will run. Okay. Let's talk about project objective first. The goal of this project is to design any ISA, like your own ISA, and then design it and then implement it. But it's not easy to design a new instruction set architecture because it is our first time. And also we don't have much time. We have only 3 weeks, but it is usually we have 4 weeks to finish. So I'm going to allow you to implement just y86 as it is, just by referring my tutorial and Bryant book and some other materials on the internet. Okay. But you can also remove some like not necessary part to make just a simple processor, but it should be it should run any program, which means your processor should be Turing complete. So you just but you can like get rid of some instructions, like some jump instruction, call and push instructions, something like that. So you will get what I'm saying about it later. So anyway, I'm going to follow the y86 sequential design as it is. So you can also refer to that in the Bryant book about chapter 4.3. Okay, and also one more thing. So I know there are so many existing implementation of y86 on the internet, so you can get that. But the thing is, during the demo, I'll ask you super detail of your implementation, and if I think you don't understand whatever you show me, then you will have a lot of penalty. Then I will consider your just copy and paste and then show me. You can use some existing implementation, but don't put whatever you don't understand. Okay, so if you cannot explain it, I consider you copied, and then you will get a huge penalty. Okay, so okay, that's about it. And let's get to the point. So this is the first week, so we are going to implement 2 things here. First is assembly to binary translator and fetch unit. But in this video, I'm going to talk about the first thing, assembly to binary translator. But why we need binary translator? Because we are making a new processor and we cannot use existing software like GCC compiler and some other utilities we use to write a C program or any program and then compile it and make a binary and then run on the real machine. But we are making a new processor and it's not physically new physical processor, so we cannot use whatever we have done. We have used on our own physical PC, like a laptop or desktop. So that's why we need at least a minimum like software that generates the binary which will be used in the logisim. Okay, but don't worry much about it because we are using y86 as it is, and actually there are tool we can refer, which is y86 program. We already used it in the lab 4, and I'm going to start with C program and then get the binary by using y8s, but we cannot directly use that, so we need some extra work for that. Okay, so first we have a C program in which we are going to run on our own processor, and it is just simple program which add 2 elements from A and B and then put the result in the C. Okay, and then I just simply converted this for loop with two go to statement and loop label, so that I can easily write assembly code which looks like this. Okay, so we are not worried about how to write assembly code of y86. I believe you can write any program using assembly code, but the thing is we don't know how to make a binary, or how to make a binary from the assembly code. But we have a tool which translate this assembly code to binary code, which YIS tool can understand. So you remember that you used YIS tool to run this binary. Okay, but we cannot. So your logisim cannot understand this format. Okay. So, but before we talk about exact format, a binary format for our own purpose, let's try to understand this binary first, because it is really a good material to understand how your binary will be loaded on the memory. Okay. So in the first part is here. So this is all about memory addresses. So memory address. And then second part around here is actually machine code. Translated from your assembly code. And then right hand side, last part is just actually comment will be ignored. But actually what it is your assembly code in the YS file. Okay. So we are not interested in the assembly code, but we want to understand how this machine code is located in the memory. Okay. So let me draw the one-dimensional memory. So this is the logical view of our memory. And then we have memory address 0x001 from the bottom. Oh, sorry, it should be 0. And then 0x001, 0x002, da, da, da. And then as we learn, one address stores 8 bits or 1 byte. Okay, keep that in mind. And then let's try to understand this format and then put machine code in the memory, more detail. Okay, so in the line 2, it says at address 0, there is a machine code this. And then next line, at address 6, there is a machine code this. But why the next address is 6, not 1? It is simple because the first machine code need 6 bytes, which means we need 6 addresses. So let's try to put the first machine code to the memory. So let me write down the machine code here. 30F046000000. So by the way, you should get familiar with hexa notation because we will play with hexa notation all the time. Okay, so let me quickly explain how to quickly convert hexa to the to understand this hexa notation. So in terms of size, so one hexa digit indicates needs 4 bits, and 2 hexa digits indicates 1 byte. So that's why I put 2 hexa numbers together and then put some space between them. Because we play with a byte level in the memory, so the 30 will be stored in the address 0, and then F0 in the address 1, 46 in address 2, and 00 in address 3, and next 00 in address 4, and next 00 at address 5. Okay, we are done for the first instruction, and then second instruction is what? This one. So 30F3, 6E, and 000000. Okay, then it exactly follow this the binary. Okay, from the address 6, we put next machine code like 30F3, 6E, and 0000 and 00. And then address would be 0x07, 0x08, 0x09, 0x0A. It's not 10, 10, it is 0A because it is hexa notation, and so forth. So we just put machine code from the address 0, and then the address and then we are done. Okay, but if you used a different ISA, then you have to consider so many things. But in our case, if we use y86 as it is, you don't have to worry about it. But you just want to put so we can reuse this format for our own purpose, but we just understood how it looks, how we understand this binary format. Okay, so it is just tells us, okay, you put machine code here, you put this machine code there, something like that. But even though we don't have this address information, right? This address information, actually we can come up with exact address where to put, right? Because we have a rule. So the first machine code will be stored in the memory address 0 first. And then next instruction or next machine code will be stored in the next memory address in the contiguous way, right? Then actually this is just extra, extra information. We can come up with this, okay? When we load this machine code to the memory. And also, okay, let me erase it. And also, then what all we need is just machine code and data to load to the memory. And the thing is, we are using Logisim to implement processor and then run it. Then we should understand how Logisim loads the initial data of the memory from the file. Okay. Okay, let me close it and then go to the binary. So we will revisit that the binary from the y86 after we understand how Logisim deal with binary. Okay, here we have just simple RAM. And then, so first we don't know how to, we can have a menu here. So like a load image. Then it pops up this menu, and then we can actually select the memory, a binary we are going to load. But we don't have binary yet, and we don't know what format we should follow. So we just play with this hexa editor. We just edit this number. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Maybe one more, like 9, A, B, C, D, E, F. Okay, I wrote 2 bytes from 1 to F, and then let's save it. Save it. Where am I? Okay, save it to my working directory, which is final project and my design. Okay, and name will be just this is memory dump, memory. Okay, we saved it. Then let's go back to that working directory. Oh, okay, not here. Where am I? Okay, here. And then we have a memory dump file, and then let's open it. And let's see how it looks like. Okay. So in the first line, we have a v2.o space and row. I think it is just a it tells the Logisim, okay, this is the raw data of memory with version 2 format. So maybe if you don't have this line in the first place, then Logisim cannot understand what it is. So when you write a binary translator, you just write this in the first line and then write down your own the machine code and data. Okay, so then there is just data in the memory. There is no address information or extra comments. It just literally dumps the data in the memory. And maybe because other data like 0000s is not present here because it is just we can just fill if there is no data, then just initialized with 0. But here, from here, let's try to redraw this memory address, a memory layout. Then let's try to double check with this figure and actually the memory in the logisim. So we start from memory address, 0, 0. And then 0, 1 and 0, 2. And then, yeah, we already know we put 1, 2 in the memory address 0. And then 3, 2, 3, 4, 4, 5, 6, 8, blah, blah, blah. Okay. So this is how we read this binary format. And then actually we are good. So it is really simple binary format. So we can edit this like this way. Okay, let me update this file with my own. Okay, I'm going to sorry, let me restore the address memory layout again. Let me finish it, and then did I mess up this file? No. Okay. Then after 9a, there is a just b, which means what? How do we write? Is it 0b or something else? Actually, I don't know. Okay, let me guess. It looks like just 0b in the address 5, and then cd in address 6, and then ef in the address 7. I don't know. Let's double check with logisim. Yeah, since I don't remember what I wrote in the logisim. Actually, is it here? Ah, okay, it's true. I think this is a good example. Okay, so maybe we can either write the 0b maybe or just b. Then logisim can understand it, what it means. Good. Okay, let's go back to here. Then we correctly redraw this memory layout from this format. But let's say we want to write something. Let's say ff in address. Let's say a. Okay. Then okay, so then the first will be stored in the address 0, and then 1, 2, 3, 4, 5, 6, 7. So like one space actually indicates the next data. So then using one space, then we can write 0, 0, because we don't want to touch anything on the address 0x8. But if we write just ff at this place, then it will be stored in the 8. So because this format does not have a way to indicate direct address place like in the binary format of matrix, sorry, the YAS. So maybe we have to put 0 zeros for 8, address 8, 9, and then for address A, we can write FF. This is how I understand this binary format. Okay, and let's save it, and then let's load this binary format in this logisim. Okay, see. And then so here after EF we have just all zeros, but I expect FF at where 9, 8, 9, 10 here. So this position I expect FF after we load the binary. Okay, let's load image here, and then where is memory dump? Okay, let's load this memory dump. Okay, there we go. So FF is updated at this moment. Okay, then, so I think we somehow understand how the logisim how the binary format of logisim memory. Okay, then we can revisit this YO file here. So then we just okay, then we don't have to put memory address information for binary format of logisim. And also maybe we cannot use this comments. Okay, let's remove comments first. Okay, I'm working on this manually, but you can make it program. And then let me remove unnecessary lines, like empty line or just done with address. Okay. And then, okay. And then what? We have just, okay, so and also we don't need address information. Remove. Okay. Well, what do you think? Is it going to just understand by logisim? I don't know. Let's try. But before, we have to write the version information in the first line. Okay, this one. Oh, and also I recognize some spaces in the beginning, so let me remove the spaces. Then just numbers, but I don't know how logisim understand this format. Just try. Okay, I just save it and then go back to the logisim and then load image. What's that? Matrix addition.yo, which we modified. And then open. Okay, it's hard to see, so let me open the edit hexa editor. But it doesn't look like the logisim understand the format we made. Okay, then maybe we need to strictly follow the format we understood. Maybe like for every address, it stores 1 byte. So we put 1 byte, and then we use 1 byte and then put space between them like this. Okay, but it will be super boring. So let me use some trick to put space like this. Yeah. So since I'm familiar with this VI editing tool, I can do it quickly, even though it is manual. But you should make an automated program to do it after you understand its binary format. Okay, but now we just understand the binary format of logisim, the logisim memory. But what about lines? Do we have to put line like this, or how many bytes we can put in a single line? Or can we put just different bytes in a same in a line, like 2 and 6 like this? Well, we don't know exact format. Just let's try. I just put a space between between bytes. Then let's try to load it again. It looks better, but let me open it again. Okay, so it starts 30 F0 blah 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 blah, and it looks good. It looks good. Okay, so we can put any number of bytes in a line. So we can put 6 line or 7 line, blah blah blah. Okay. Yeah, so logisim is a little bit smarter than I expected. So it is good. So then what? it's done. So this is the one example of binary we made. I mean, this is the binary of, where is it? Binary of, yeah, this assembly code. Okay, so then what you are going to do is just write your own program using y86 assembly code, and then run YAS tool to make a binary format for YIS, and then, but instead of using YIS, using your own tool, you just manipulate YO file for logisim memory format like this, and then we are done. Okay. Okay, it is done, but I have one last thing for you to mention and talk about. So here, so in the next video, like about fetch unit, I'm going to talk about that, but let me talk about here because it is also related with binary format. So, so here we can change the data bit, like 8 bits or 16 bits. So let's try to change this bit to 16 and then see whether it understands the binary format we made as it is. Okay, so I cleared content first, yes, and then load it again. This one. Then let's see, edit contents and then see. Oh, is it correct? We want to load the correct way we want to load. So see, in the first place, there is a 0, 0 and 3, 0 and 0, 0 and F0 and 4, 0, 0 and 4, 6. But this is not what we want, right? So when we draw this layout, using this way, then in address 0x00, it stores 0, 0, this part. And then in the address 0, 1, 30, 30 is 30 is stored. But when we read binary format for the first time, 30 was in 0, 0. So this memory, this load, we change the data bit size, then we should change format as well. Okay, so what I'm saying is here, so since when we use 16 bits as a data bit, then when we write a binary format, it also follows same rule. Okay, so then since we want to put 0, 0 in the first address, then okay, again, so when we use just 30, then it understand like this way, 0, 0, 0, 0, 3, 0. And then first, in the first address, 0, 0 will be stored, and then second address 1 will store 0, 3, 0. But that's not what we want. So maybe our format should be changed like this. So we put 30 F0 together without space, and then put next 16-bit data here. And then we put, in short, we put space in between 16-bit data. Okay, then we need to remove the address spaces in the 2 bytes, like 1 byte, and then also remove this, the second, this space, and then put 2 bytes together. 2 bytes is actually 16 bits. Okay. And also this one, see, this one should be handled, I think. Let's put this with, yeah, previous one, like this. Okay, looks good. And then let me store this, save it, and then load it again. Loading. Okay, good. It looks better. Okay, since 30 is in the first address. Okay, then let me open the hex editor. Okay, looks better. So 30 F0 4600 in the consecutive memory addresses. And then second is 30 F0 6E 00000 in the next consecutive addresses. Okay, looks good. So I believe you understood the format of this binary for Logisim to understand. Then we are almost done. So based on this understanding, the format of this binary, you can, what's that? You can just translate, okay, since I already removed, so let me run this quickly. So let me change this file yo to something else. And then run this again. Oops. Okay, so I'm working on some other place. Okay, so in this laptop, I don't have YAS2, but anyway, you remember how YO initial YO file, but from that we get this. But I did it manually, but I'm going to I'll expect you to have the automated tool to convert this to that. Okay, but still it's okay if you super worry about the implementation of y86 processor. You just do it manually, and then if you have time, then do it at the last moment, and then you will get some what's that better credit. But this is not super important for our course, so you can just do it as I did, like manually, and then work on the fetch unit first. Okay, so it's all about the first work, the binary translator, like assembly to binary translator. So I will see you in the next video with fetch unit. Bye.